In the past, we have looked at the motion of objects moving in a line, straight line motion, and talked about what causes changes in that motion, that forces determine the change in object's motion, F equals ma. That's called Newton's second law. There's a similar law for rotation, where instead of talking about forces, we have to involve torques. Instead of talking about just mass, we have to include how that mass is distributed about the axis point, so that's I, inertia, and then we also wouldn't talk about the linear motion of the object, we would be talking about the angular motion, and so the change in that angular motion would be the acceleration. Let's look at some conceptual ideas related to this formula. So here we have a little girl pushing along the edge of a ride at a playground, and as she exerts her force at a distance away from that red axle, she exerts a torque. She produces torque on this ride. Now, that will accelerate the ride. That will make it spin faster and faster. If she wants to get it up to a really good speed more quickly, if she wants to have a greater angular acceleration, she's going to have to find a way to increase her torque. Maybe she can push harder or get a friend to help her out. Okay, so we can see from this equation that the greater the amount of torque, the greater the acceleration, angular acceleration. Whereas if we consider this man lifting and jiggling around a barbell, he'll find that the first barbell, the one on the left, is a lot easier to rotate. And that's because the inertia is somewhat smaller than the one on the right. So if we compare the left picture to the right picture, where the inertia has increased in comparison, he might be able to exert the same amount of force, and he's doing it in the same way, so the same R. But because the inertia has increased, the barbell will not jiggle around as much. There will be a smaller amount of angular acceleration, a smaller change to the angular motion. So this is what we're going to work with today. We'll do a problem in just a few minutes. We will need to put all of our skills to use. So we've learned how to calculate torque. We have learned how to calculate rotational inertia using ideas of particles, using ideas of formulas for shapes. And we have learned how to describe changes in an object's motion when it's rotating, the ideas of angular acceleration. So all of these three skills will be put to the test today. If you need to take a minute to write down this formula in your notes, or this problem into your notes, please do so. This is very similar to what you did in the part 1 of the lab a couple of days ago, where we had a fixed pulley and pulled on a string, and that caused that pulley to rotate. But this is a much larger pulley, mass of 5 kilograms, diameter of 30 centimeters. That's, a ruler stretched across it. So we are looking to determine the angular speed of this pulley after it's been pulled. And so what we're looking for is a value of omega. To get there, we are first going to need to determine a value of angular acceleration so that we can use that time that we're given and the fact that it started from rest. But where is that value of angular acceleration going to come from? That's where we'll need to calculate both the torque that our pulling force creates and I, the rotational inertia of this disk that is moved around. So let's go through these steps. Calculate torque, calculate inertia, combine those together to find angular acceleration, and then use that to find omega, the rotational speed. So to calculate the torque, we need to know how much force, that's our 18 newtons. We need to know where that force is being applied, and it's right at the edge. So the r here really is the radius of this object. We were given the diameter in centimeters, so we'll divide that in half and convert to meters. And then our angle will just be 90 degrees. Kind of a cool thing about pulleys and why they are so useful is that no matter how you yank on that string, the string will always be tangent to the circle. So it will always be perpendicular to the radius. And so we can just let that drop out. The inertia needs to be calculated using a formula for a shape. And we would look up that the formula for a solid disk is 1/2 the mass times the radius squared. Again, using that 0.15 meters as the radius. We got a rather small value, and that is measured in kilogram meters squared. An unusual unit, but this is often a value that's used to find something else. So it's just not commonly known. Next step is to combine these two values into a value of angular acceleration using the formula that was just introduced. And so we just have that one torque, so our net torque is just 2.7 Newton meters. Divide by our inertia, we get 48 radians per second squared. Now, maybe you're looking at those units going, how did that come out to be radians per second squared? Well, a Newton is calculated by taking a mass times an acceleration. And so the unit of newtons must equal the unit of mass, kilograms, times the unit of acceleration, meters per second squared. And so you can see how everything cancels out except the per second squared. And here's where our magic unit of radians would pop back into the picture. All right, last step then. To find the angular speed, we know the time, we know it starts from rest, and so we can just use our omega equals omega sub 0 equation to see that the angular speed is 72 radians per second.